Okay, question 8. Not easy, but not too bad for question 8. So firstly, we have a complex number z, cos theta plus I times sine theta, and we need to show that the real part of 1 plus z over 1 minus z is equal to 0. Okay, so firstly, let's start with 1 plus z over 1 minus z. What is that? Well, it's 1 plus this over 1 minus this. So it's 1 plus this over 1 minus this. It's minus cos theta. I'm going to put minus, be careful guys, it's minus I times sine theta. Okay, now hopefully guys you remember, if I want to, well, often when dealing with complex numbers, you want to get rid of the imaginary part from the denominator, because if I want to find the real part of another complex number, which is ultimately this, I can't have this imaginary number in the denominator. So I want to get rid of that, a bit like you want to get rid of the square roots from, or rationalizing the denominator when you've got a square root underneath the line. I do that by multiplying above and below by the complex conjugate of the denominator. Now the complex conjugate is, well, if the complex number is a plus bi, the complex conjugate is a minus bi. And this is, well, a is the real part and bi is the imaginary part. The real part of the denominator is 1 minus cos theta, so I'm going to multiply by 1 minus cos theta. But instead of plus bi, I have minus bi, so I'm going to the complex conjugate would be plus bi, which is I sine theta. So I'm multiplying across, multiplying above and below by the complex conjugate of the denominator. So this has to be, sorry, that's a cos. So this has to be exactly the same as that. Okay, and it's that multiplied by this multiplied by this. Okay, that's the first step. Possibly the hardest step. The rest now is just, well, again, it's not easy, but it's just algebra. So I need to multiply this by this and this by this. You could just do the first term times the first term, first times the second, first times the third, second times the second, second times the first, second times the second, second times the third. Okay, actually, why don't we do that for the denominator? So I'm going to do 1 times 1 is 1. 1 times cos theta is minus cos theta. 1 times I times theta. So that's just 1 times all of this. Now I do cos of theta times all of this. So I do plus cos theta minus cos squared theta, and then plus I sine theta cos theta. And then finally, I have this times this, so plus I sine theta minus I sine theta cos theta, and I'm just going to move this, guys, over here. And the final term would be, so I times I is minus 1, so it's going to be minus I times I squared is minus 1, and then I have to do sine squared theta. So that's the numerator. The denominator, I'm not going to multiply it out as much, because if you remember, because I'm multiplying across by the complex conjugate, I'm just going to get this squared minus this squared. So I'll show you what I mean in a second. So it's 1 minus cos theta squared minus plus sine squared theta. Now the reason is because, look, the denominator, I'm essentially doing a plus bi times a minus bi. And what I get when I do a plus bi times a minus bi is I get a squared minus bai plus bai, and then minus b squared I squared. These cancel, and I'm left with a squared minus, and because it's I squared, it's minus 1, so it's minus minus, which is plus. That's why this is a plus here. And then the b squared is just b squared, and that's my sine squared. So in this case, a is my 1 minus cos theta, and b is my sine of theta. Okay, I'm going to get rid of that. You don't have to show that. That's just a nice thing to remember. Okay, anyway, that's the denominator. All I need to show now is that this numerator is equal to 0. So I have a cos theta, I have a minus cos theta and a plus cos theta. They cancel. I have a I sine theta cos theta minus I sine theta cos theta. Okay, that's not bad. I then have an I sine theta. Okay, I have a 1 here. I have an I sine theta and an I sine theta, so that's plus 2 I sine theta. And sorry, I need to show that the real part of this, so that's fine. So it's 1 plus 2 I sine theta, and then I've minus cos squared theta minus sine squared theta all over 1 minus cos theta squared plus sine squared theta. Okay, so this is 1 plus z over 1 minus z. What I want to find is the real part of 1 plus z over 1 minus z. So the real part would mean it's this without this imaginary part. So the real part is just 1 minus, and then this is cos squared theta, and I'm actually going to factorize it at this point, guys. I'm going to take out that minus 1, so it's minus cos squared theta plus sine squared theta all over this same thing, 1 minus cos theta squared. I don't have to do anything with this denominator. I don't have to multiply it out or anything, because it's just the denominator. If I can show that this is 0, then we're all good. And it is, because this is equal to 1 minus 1, because cos squared theta plus sine squared theta is 1. That's the Pythagorean identity. So it's 1 minus 1 over this again, cos theta squared plus sine squared theta, and this equals 0. And that's what they wanted us to show, that the real part equals 0. So we've shown it. Q, E, D shown. Okay, not too bad. Look, it's definitely a hard question, and in an exam there's a lot of mistakes to be made there, but it's one of those ones that I would categorize as familiar difficult.